First of all, this electric force is acting on this charge here in the formula. This is the definition of the electric field. That's the test charge. And this electric field is created by all the other nearby charges that aren't the test charge. The test charge doesn't push on himself. It's the other charges that set up the field. Now, because these charges, the one here and the one in the back of the room, are pushing or pulling on each other, they have to take turns being the Klingon and the Captain Kirk. When I'm worried about the force on this charge, it's the Captain Kirk, it's the test charge, and the other charge, the source. When I'm worried about the force on that one back there, it's the test charge, it's the Captain Kirk, and the one up here is taking its turn to be the Klingon or the source. And so it often comes down to which one is acting as the source. And that's what we're going to concentrate on today. One thing that I need us to get down...
If there's only the two charges acting on each other, by the third law, isn't the force equal?
They are. They are. And we'll get to that a little bit later today. Often there's more than two. And so we have to worry about more than one Klingon. Now, something that you can take to the bank. The electric field will always, always, always be away from a positive source. Because think about what an electric field is. An electric field, first of all, what's at the x here? What is at the x? Nothing. Empty space. Nothing at all. That x is just a placeholder. The electric field has some waffle words. The electric field is the force that would act at that x if I were to reach into my pocket and pull out a 1 coulomb, a plus 1 coulomb, and put it there. But I didn't really. That would kill me. I just do it with my mind. In my mind. Okay? I pretend to put a plus 1 coulomb there. Now, if this is positive and that's positive, how's this going to be affected? Is it going to be pushed that way or pulled that way? It's going to be pushed away. It's always going to be away from a positive source. On the other hand, it's always going to be towards a negative source. Again, I pretend to reach into my pocket, I pretend to pull out a plus 1 coulomb, and I ask what force would it have felt had I really done it? And since this is positive and that's negative, it would be an attraction. So, that much you can hold on to. If it's feeling like there's just too much, there's too many ideas, those are only two. The electric field is always away from a positive source towards a negative source. If you miss that on the exam, we'll try, but we can't feel sorry for you. Okay? We can't. It's too easy. You go to an anatomy class, you got to remember what? There's 16 bones in the body? Something like that. Okay. The size of this field is given by Coulomb's law. I'll write that on the board. Okay. Now, in 3 dimensions, and that's what we're going to be dealing with in these problems, it's impossible to name one direction the negative direction, and one direction the positive direction. That leaves an infinity minus 2 directions to name, and I'm going to run out of names. So what we're going to do when we use this formula is we're going to use it to find the strength of the electric field. the magnitude, how strong it is. That's always a positive quantity. And so we never put the sign of the source charge into that equation. Okay? So, I move this over here a little bit. Now, the hardest part about using this equation is knowing which charge in the problem is the Klingon, is the source. How do you recognize the Klingon? Well, that's what they look like. Okay, now I've got a handout here that's going to help you to recognize the Klingon. This is the equation for the electric field. The equation for the electric force is also the definition of the electric field, that first equation. And if you put this equation and that equation together, what you get is that force equation that looks like the gravitational force. So this would be the test charge here.
And that's the source charge?
Yes, see the electric field is this and this and this. And if you multiply that by the test charge, you get the force.
The big Q is the source charge?
I'm sorry?
The big Q is the source charge?
Yes. The little q is the test charge. However, in problems, I might not give you that hint. I might not make the source charge capital and the test charge lowercase. Indeed, in this handout, you're going to find that the different charges take turns being the test charge. And so we have to do a careful reading of the problem to determine which is the test charge and which is the source charge. Let's start with this part A. We have two charges that are separated by 20 centimeters. One is a positive 3 nanocoulombs, nano being 10 to the minus 9, and one is a negative 6 nanocoulombs, or negative 6 times 10 to the minus 9. Now, listen carefully to the wording of this question. What is the electric field strength, the magnitude of the electric field, at the location of Q1 due to Q2? Now, in this formula for the electric field, I have K, which is 9 times 10 to the 9th Newton meter squared over Coulomb squared. I have room for one charge. And the question is, if I'm answering this question here, which charge, Q1 or Q2, do I care about? Which charge is the source creating the field? Now, another way of asking it is, would this change the problem at all? Could I rewrite the problem to say, what is the electric field strength at the location of the elephant due to Q2? Would that be the same question that I had before? Yeah, Q1 was just a placeholder. It was an old stump on the side of the road. Okay? Now I'm using an elephant instead. What should be clear to everyone is that the words due to Q2 make it the Klingon in this problem. It is the source. It is creating the field. It is the Q that goes into my formula. And when I put it into the formula, I put it in as a positive value. 6 times 10 to the minus 9 coulombs. I don't put a minus sign there because I'm looking for the strength. Now, let's do that. Let's get rid of the elephant, get rid of Q1, and put an X there. The X again is just a placeholder, an address, a number on a mailbox. Now, if this is my source and it's a negative source, the electric field over here at the X is going to point what way? Towards the negative source. Okay? And the size is going to be given by Coulomb's law, where we plug in the charge as a positive value, because we already know the direction. We're looking for the magnitude. And what we get when we put that in our calculator is 1,350 newtons for each coulomb to the right. Now remember, the interaction between Q1 and Q2 is a two-step dance. Okay? We just did the first step of the two-step. The first step. Now that Q2 has set up a field at the location of Q1, we ask part B, what force does Q1 experience? Now folks, I find that a lot of people have a hard time understanding the direction of the force. It comes from this vector equation here. If the electric field is to the right, and the test charge, the thing that's being pushed, is a positive test charge, then the force is going to be in the positive right direction. If the electric field is to the right, and the test charge, the thing being pushed, is a negative charge, then the force, the actual push or pull, is going to be in the negative right direction. Well, what's negative right? Left. Is it wrong? No, it's left. Okay? It's left. So that's another principle that you can take to the bank. Whenever the test charge, the Captain Kirk, the thing that's being pushed, is negative, the force will be opposite the electric field that's pushing it.
Say that one more time.
Whenever the test charge, the thing that's being pushed, is negative, the force will be opposite the field that's pushing it. Because if I take a field to the right and multiply by a negative number, I get a vector to the left. Okay, if you take a vector and multiply it by a negative number, you change its direction by 180 degrees. Are we on the bus? Now in this case, Q1, first of all, Q2 has done its job. The first step of this two-step dance was for Q2 to set up a field. It's done that, so we don't need it anymore. The field is going to push on this Q1, and Q1 is positive. Since it's a positive test charge, the force is in the same direction as the field. Well, think about it. The field is how hard a +1 Coulomb would be pushed at that location. If I've got a different positive charge, just a different size positive charge, it's still going to be pushed in the same direction, right? So the force would be to the right. And the size would be given by this definition of electric field. And that would give me 4 times 10 to the minus 6 newtons to the right. Okay? Check that your neighbor's on the bus. We're about to do this again. If your neighbor didn't quite understand, we got one more kick at this can, and then the can's forever done. Okay? Okay. It was just pointed out that these forces that we're calculating are very, very teeny tiny. And yet we have to remember that typically we're pushing on a proton or an electron. And a proton has a mass of 10 to the minus 27 kilograms. An electron has a mass of 10 to the minus 31 kilograms. And so we end up with huge accelerations with these size forces. Okay? Now, let's go to part C. This should be obvious after parts A and B. What is the electric field strength, listen carefully, at the location of Q2 due to Q1? Which charge do we care about?
Q1.
Yes, this time it's Q1. Putting an elephant at that location of Q2 does not change the problem. It's just a location we care about. The elephant is a placeholder. Now notice what just happened. In part A, Q2 was the Klingon. In part C, now that we're caring about the force on the other charge, Q1 is the Klingon. They trade off in the role that they play in this little feature film. Okay? So, I replace, it's due to Q1, so I get rid of Q2, I get rid of the elephant, and I just put an X there to represent the address, the location. Now, my source is a positive source. The electric field that it creates over here at the X is going to point away from the positive, which would be to the right. And now when I use this formula here to find the size, I would put Q1 in here. The size of Q1 is half the magnitude of Q2, so it shouldn't surprise me that I get a field that's only half as big. Okay? Now, again, that was just the first step of the two-step dance. We're looking for the force on Q2. We started by letting Q1 create a field. And now that field is going to push or pull on Q2, and that's part D. Part D asks, what force, not farce, it's real, what force does Q2 experience? Okay? Again, Q1 has done its job. It set up the field. We don't have to worry about it anymore. We put that Q2 there, and it's a negative Q2. What direction will the force point if the electric field is pointing right and the test charge is negative? Left. It'll point in the negative right direction, which is left. Okay? Again, think of it in terms of the electric field. The electric field, if you think about it, is the force I would have if I put a +1 coulomb there. Well, if a +1 is pushed this way, wouldn't a negative charge be pulled the other way? Okay? So, the size of that is now given by the definition of the electric field. Notice that I did not put a minus sign in there. I already know the direction. I used my gut to get the direction. I'm just looking for the magnitude. And the magnitude is 4 times 10 to the minus 6 to the left. Okay, we just went through the process twice. Once finding the force that Q2 put on Q1, and one finding the force that Q1 put on Q2. Okay. See if your neighbor's on the bus, please. Do a buddy check.
I love it. I love the lecture.
Let me summarize the first 4 parts of this handout. What I found is that the electric field due to Q2 over here was 1350 newtons per coulomb to the right. The electric field due to Q1 over here was 675 newtons for each coulomb to the right. These electric fields are equal and opposite by what law? People. They're not equal. They're not opposite. And that's my point. There is no Newton's third law for fields. Newton's third law applies to forces, honest to goodness pushes and pulls. And when we found the force that was acting on charge 2, it was that big to the left. When we found the force that was acting on Q1, it was the same size to the right. And we would label these. This is 2 pulling on 1. This is 1 pulling on 2. They are equal and opposite by Newton's third law. Always. Always. You can't make them not equal. If Q2 was positive, then these forces would be repulsive forces, but they would both be in the opposite direction. And so you would still have them equal and opposite.